Good morning. So, we will continue where we stopped in the last lecture about model calculation. So, these are the topics in red color we covered. We will continue with the model calculation aspects, and this is the problem. Okay, we have done various aspects for given the ratio, gear ratio and the torque aspect. We have done the ray diagram, select the gear type, done the ray diagram, kinematic diagram, also we've done the suitable materials. Now finally we are in model calculation aspect, and this is the equation we have used based on the bending aspect, model equation, and also based on pitting aspect. In fact, as I said, since the pitting stress is very high, higher than the bending stress, would be prefer to use pitting stress based calculation for your model aspect. Of course, there I talked about the psi factor, which is a frame factor ratio, or else we can say a structural support. We have choose the psi value as a 30, we have taken the lowest value. Okay, and we got our model calculation. The model what we got is we have taken the model m equal to 2.412. This is what we got it. Yeah, this is when you have a psi equal to 30 and your factor of safety s square equal to 1.5. Just wanted to show the relationship between your factor of safety as well as the structural support or frame factor ratio. Yeah. So, this is your factor of safety for its various value, your structural support psi, right, just extend it. Assuming your factor of safety 1.5, 2, 2.5 and 3, the structural support 30, I will take the lower limits 40 or maybe 35 and 40. Okay. So, this should be as we got 2.41, 2.65, 2.86, 3.303, 2.29, 2.52, 2.72, 2.89, 2.19, 2.41, 2.60 and 2.76. So, what is your observation? Assuming that you have fixed a factor of safety 1.5, right? If you choose and if you vary your structural factor as you increasing the higher value, structural support value, your model is reduced. You can see the trend is the model is reduced. Okay. Otherwise, you fix structural support 30 and you change your factor of safety, right. When you change the factor of safety 1.5 to 2.5, you could see there is an increasing trend in the model calculation. Okay. So, from this your observation, you have to do optimization. Okay. The purpose is you do not want to have the failure aspect, that is one thing. At the same time, you have to look after the material, the weight, the volume, that is also very important. Higher the model, what happened to your the gear size will be increase, right. So you have to be very what do you say that you can't have too much factor of safety, same time you cannot have a very high structural support also. You have to do some a kind of optimization and get the best out of it, like. So after subject, just wanted to inform you, part of my research work I do optimization. So I've done a lot of gearbox optimization to meet the tribological constraint, including pitting stress, bending stress, and reduce the volume. Like that, I've done the extensive work and published in Mechanism Machine Theory, one of the top impact journal paper. You can refer my website to understand more about the optimization aspect. Okay, right. So what was the teeth? We choose the profile aspect, right? This is the one. Then what we have done, even though we got 2.412, we have to choose the standard one. So what we have done, we have taken the m equal to 2.5 mm based on the standard aspect. Okay, so this is the model we have chosen. In fact, if you move further above the things, remember we have chosen the full depth, right? Pressure angle 20 degree, spur gear, a full depth. So this is what you see that. So this is your other parameters of the gear profile. This is for addendum, dedendum, clearance, working depth, and hole depth, and tooth thickness. All those information you have to follow based on the what profile you have chosen. We have chosen 20 degree pressure angle with the full depth system aspect. So in fact, further if you find out the what is the value, the based on the thing, m equal to 2.5 mm, that is the module value. Fine. Your addendum 3.125 after multiplying. Okay, I am just giving the right away values, and dedendum 0.625 millimeter, and working depth means from the top space to is a base circle, right, to the base circle or pitch circle, the working depth. Okay, the working depth 5 mm, the hole depth, these are the standard nomenclature for gear, 5.625 millimeter, and tooth thickness T 3.927. Okay, this is the millimeter. So one parameter is missing. Which parameter is missing? Is a face width, right? That face width parameter is missing. Yeah, we need to find out what is the face width. Okay. Now we will move on. So this is what we have chosen, right? Remember, for the first gear we have chosen the first gear we have chosen the psi ratio, in terms of psi ratio B by m, right? We have chosen the B by m as a 30, right? A 30 we have chosen. So if you substitute model, we know 2.5, then what of the face width for the first shift gear? That should be 75 mm, right? That should be 75 mm. Okay, that is 75 mm. So 75 mm, which gear? Gear number 12. Remember, please check your kinematic diagram. First gear is meshing gear 11, right? Gear 12 mesh with the gear 11. That is your first gear shift. First gear shift. Maybe I can write gear 12 mesh with the gear 11. Okay, so this is the face width of 12 equal to 75 mm. Okay, right. Look at this graph. Okay, this is taken from automotive transmission system, and as you are aware of that, Higher the speed, the torque lower, okay, but the lathe shaft has a constant torque, okay, but the stresses will be different. The stresses will be different. So, in order to accommodate stresses, we have to play around the changing the different phase width for each gear. So, the first gear we have done using the structural formula. Second gear we can choose 0.4 for second gear. This is a B by D ratio, not the B by M. This is a B by D ratio as a 0.4. Okay. The remaining, they are almost same, right? This third, fourth and fifth, they are almost in the range of 0.3. So, what I could do for third, fourth and fifth gears, right? Gear shifts, this is a gear, not gear, gear shift. I will choose B by D ratio as a 0.3. B is the phase width, D is your pitch diameter. Okay, D is your pitch diameter. So, we have done B for the first gear shifting. Now, we need to do for other gear shifts. Before proceeding, we should know the number of teeth for the each gear aspect, right? As you are aware of that, we have done the gear teeth calculation and found some gears are less than 17. So, what we have proposed, without altering, changing other parameters, we double the gears, number of teeth gears. Okay. In fact, the number of teeth in all gears, right, all gears of this gearbox, okay, with Z11, Z1 34, Z2 68, Z3 28, Z4 74, Z5, okay, 32. This is the where we had a 16. Z5 was 16 earlier calculation. So, once we multiplied, we got 32. Z6 70, 7, Z7 38, this Z8 equal to 64, Z9 52 and Z10 equal to 50, Z11 66, Z12 36. Okay. And if you if you do summation of each Z1 plus Z2, that should give how much? 1 or 2. So, all the 34, 68, 28, 74, 32, 70, 38, 64, 50 to 50, all teeth are matching. Okay. All teeth are matching. Now, we will do the calculation for the second shift gear. Gear shift. Please refer your kinematic diagram where gear 10 mesh with gear 9. Yeah. So, M we know that M equal to 2.5 mm, that is already known to us. So, now M equal to D10, I am giving the number based on the things, and Z10 equal to, right. From here we want to find out what will be the pitch diameter. 2.5, Z10 will be 50, okay, and that should give me 125 millimeter. This is for second gear. Yeah. So, then your B by D ratio we have chosen what? B by D ratio we have chosen as a 0.4. In that case, my B10 should be, I am talking about gear 10, 125 already we know that. That gives me 50 millimeter. Look at the difference. Earlier we had 75 for gear number 12, the phase width. Now, gear number 10, the phase width reduced to 50 mm. Okay. You may ask question, why I choose the gear 10, why can't be gear 9? Gear 10 is the drive gear, right? That is the one which is transferring the force from gear 10 to gear 9. That we always should focus about the drive gears rather driven gear aspect. Now for third gear, gear shift, right. Here is gear 8 mesh with gear 7, okay, and we have chosen the B by D ratio equal to 0.3, and as usual M equal to D8 Z8, okay, and we want to know what is that D8, 2.5 times into 64, Z4 equal to Z64, that should give me 160 mm, 160 mm. Then the corresponding B8 equal to 0.3 into 160, I would expect 48 mm is the phase width. This for third gear. So similarly, we will go do for fourth gear also. Fourth gear shift, your G6 mesh with G5. As usual, we have taken the B by D ratio 0.3 0.3, just the ratio factor. M equal to D6 Z6, right. Then D6 equal to 2.5 into 70 number of teeth for gear 6, 175 mm. Then B6 to D6 is a 0.3. By doing that, your B6 must be 0.3 into 175. It gives me 52.5. So we will make this approximately 53 millimeter. Okay. For fifth gear, gear shift, where your gear G4 mesh with G3, okay, G3, M equal to as usual D4 by Z4. So from here if you calculate D4, 2.5 times 74, 185 millimeter. Then B4 D4 we have chosen as a 0.3. From here your B4 would be 0.3 into 185, it gives me 55 millimeter. Okay. Now we got the phase width for each gear shifting, right. Gear shift 1, 2, 3, 4, 5. In fact, if you do a gear shift, we can do the tablet gear shift on the phase width, right. Phase width is in millimeter. If you tabulate them, right, this is 1 is giving 75 mm, 2 50 mm, 3 48, 4 53, then 5 is 55. So can you see that what is happening as your gear changes, right? Now gear change is happening, your phase is reduced. Of course, you may ask question. The first two gears, first gear I understood, and second is and third are reducing. But what happened when the moment it goes to fourth and fifth gear? It's again increasing. Now you know when you refer that B by D ratio, it's slightly above 0.4. Now you know that, okay, because the sizes changes. To accommodate, the phase width will increase slightly for the higher shift gears, right. Interestingly, this is as explained earlier, taken from our building machine design section in the foyer where you would see this is the manual transmission sliding gearbox. Of course, we are doing the problem for manual transmission constant mesh, not the sliding mesh, but doesn't matter. So, can you tell me what are the gears here? So, this is your input shaft, right? This is coming from the input shaft. Straight away you could see your reduction here, you can see the reduction. Then you have this is your first gear, right? The first gear when slide, this is your first gear, right? And this will move to slide, make a contact. Then this is your second gear, straight away has a thing, and this is your third gear. Okay, this is your third gear. The fourth gear, I guess, this straight away connect your input shaft, right? That's why you could see there is no space also. There is no space also, right? It's straight away connect things. Could you please observe what is that happening? The first gear. Look at this, the face width. How big the face width, right? Second gear you can also is slightly reducing, right? You can see the face width is reduced, and even for third gear also reduced here. Then this is your first gear reduction where coming from the things. So, by choosing the face width also, the another advantage is you are reducing the shaft length. So, you can see these multiple benefits. If you had been fixed face width as a constant for all the gears, you are having a more mass, right? Not only that, and also you are adding the length of the shaft, which is against optimized compact gearbox aspect. That should be avoided. So, by this is the way you need to do. Let me put one more question. Sometime, okay, do you think the face width should be equal for both meshing gears or can be variable? It can be variable. It can be variable. Need not be face width are equal. Okay. So, wherever the power transmission occur, right, where is going to be more stress here, the receiving side, the gear also can have a higher face width. That also possible. So, design is the multiple solution. It's not a single solution. It's a multiple solution problem. Depends on what is the requirement. Based on your requirement, you can use different solutions. Okay. So, this is the sliding mesh, and since I talked about shaft, I just wanted to give you another information. Okay. The center distance, you can see this is a standard center distance. We have chosen, there is no concept in the problem about center distance. So, we are free to choose the model calculation without worrying about the center distance aspect. Okay. Let me ask you a question, what is the center distance now? Can you tell me what is the center distance? We know the module, right? We know the module. So, we have gear number 12 and gear number 11. So, tell me what is that center distance we are going to have, right? And the module is given m equal to 2.5 mm, right? M equal to 2.5 mm, that is there. How do you calculate center distance? Center distance equal to A equal to m into Z11 12 by 2. Okay. Thank you. So, 2.5 Z11, I know what is that Z11, 66 plus 36 by 2. So, what is the answer you are getting? 127, right? 0.5 mm. Okay. So, okay, now we know that 127.5 mm we got the center distance. So, do you think that is standard center distance? We have 125, you can see that preferred is 125 given. So, the next preferred is 160, or else that is too big, right? That is too big. Maybe you can choose 140 also. Okay, but in this problem there is no constraint for center distance aspect. In assignments in the exam, if you get center distance constraints, you have to follow the standard aspect. Okay. This is taken from Vauxhall 6+1 gearbox. Look at this configuration. It's nicely arranged, right? As I said, one of the lecture I mentioned, multi-stage, where you have one input will have two output shafts, right? You can see this is taken from the brochure of Vauxhall, and there are, you can see that there are three shafts are arranged. So wherever you have a length constraint, right? In that constraint, you can go for two output shaft aspects. You can see here, this is the arrangement. The same thing with the kinematic arrangement. So you have to be very careful. The gear, common gear should be, will have a required gear ratio, one gear for both output shaft. Such a way that you have to design. I think I'll stop now. Thank you.